Okay, notes 10.7, alternating series test. So the alternating series test, we're trying to check if the series is alternating between signs. So is it going positive to negative, then back to positive, or negative to positive, and then back to negative? So it says if a sub n is greater than 0, then the alternating series, the summation of n equals 1 to infinity of negative 1 to the n power times a sub n, and the summation of n equals 1 to infinity of negative 1 to the power of n plus 1 times a sub n converge if both the following conditions are met. So the first condition is that the limit as n approaches infinity of a sub n must equal 0. The second condition is that the absolute value of a sub n plus 1 has to be less than or equal to the absolute value of a sub n for all values of n. And so ultimately what this means is that the next term in the series has to be smaller. Okay, or another way to view this is a sub n is decreasing. Okay, so that's what this inequality means. So it says ways to check if a sub n is decreasing. So ways to check and prove this second condition. So it says the first way is to take the first derivative and see if it's negative. Okay, this is the hard way. Don't do this way. Okay, don't do this. This is hard. Okay, the second option, it says usually it's obvious, and what that means is we plug in numbers and then we check to see if every number that we plug in is decreasing. Another way is we can manipulate this inequality. So we could rewrite this inequality to be a sub n minus a sub n plus 1 is greater than or equal to 0. Or we can rewrite this as a sub n plus 1 over a sub n is less than or equal to 1. So the most common one that is used is this one here that I'm highlighting. And that's the one we're going to use most in the notes. Okay, so let's look at number 1. Number 1, we have the summation n equals 1 to infinity, and then we have negative 1 to the power of n. So notice this is a alternating series. Okay, and then we have our 1 over n, which is our a sub n. And remember from previous notes that this is a harmonic p-series. And if you remember from those notes, we know that a harmonic p-series is going to diverge. But since this is an alternating harmonic p-series, we're going to have to check to see if this still diverges or if it's going to converge. So in order to check this, we check both conditions. So condition number 1, remember the limit as n approaches infinity of a sub n must equal 0. So this is the limit as n approaches infinity of 1 over n. We know for obvious reasons that that goes to 0. So the first condition is met. Condition number 2, we need to check if a sub n is decreasing. And so one way to do this is the obvious way that they mentioned, and that is just plugging in one number at a time. So for example, for 1 over n, if we plug in 1, that would be 1 over 1. Then we can plug in 2, 1 over 2, then 1 over 3, then 1 over 4, and continue on forever. Notice that 1 all the way to 1/4 is decreasing. It's getting smaller. So since it's decreasing, that condition is met. And so since both of these conditions are met, we can conclude, so therefore, this series converges by the alternating series test. So if we were to see this again, we know that an alternating harmonic p-series always converges. Okay, let's look at number 2. Number 2, again, we have an alternating series from right here. This is an alternating series. The only difference is since this is to the power of n plus 1, that means that first number is going to be positive. Okay, so when we had just negative 1 to the n power, that first number is going to be negative. So first number, and this is not super important, but it's still good to know. First number is positive. Okay, that means everything else, this is our a sub n. Okay, and this one is not an obvious series, just like number 1 where we knew for sure that was a harmonic p series. So we still go through the 2 conditions. And so number 1, we're trying to see if the limit as n approaches infinity of a sub n, okay, is equal to 0. Okay, so instead of rewriting this whole thing, in order to see if this is equal to 0, remember we only really care about the numerator and the denominator's highest degree. So on the top we have n, and on the bottom we have n squared. Okay, so if we plug in as n approaches infinity, the denominator is increasing much faster than the numerator. Okay, so really, we're going to have a bigger denominator, okay, which implies that this limit is going to equal 0, which proves our first condition. Okay, the second condition, okay, notice this is not as simple as us just plugging in a number. I suppose you could plug in a number. You could plug in 1, then 2, then 3, etc. Or we could use the other way to check if a sub n is decreasing by using that ratio of a sub n plus 1 over a sub n is less than or equal to 1. So that's what we're going to do. Okay, so we're trying to see if this is less than or equal to 1. Well, we know this is a sub n, so what we need to find first is a sub n plus 1. Okay, and so all that means is anywhere there's an n, we're just going to add 1. So this is n plus 1 plus 5 over n plus 1 plus 2 and n plus 1 plus 3. Okay, notice anywhere there was an n, I replaced it with n plus 1. Okay, then I can simplify that. That becomes n plus 6 over n plus 3 times n plus 4. Okay, that is a sub n plus 1. And so putting that in the ratio, that is n plus 6 over n plus 3 times n plus 4 divided by n plus 5 over n plus 2 times n plus 3. Or that's the same as multiplying by the reciprocal. So n plus 6 over n plus 3 times n plus 4 times n plus 2 times n plus 3 over n plus 5. When we do that, n plus 3 cancels out. And so we can continue to simplify this by multiplying the rest out. So we have n plus 6 times n plus 2. So if we FOIL that, we get n squared plus 8n plus 12. And then on the bottom, if we FOIL n plus 4 and n plus 5, we get n squared plus 9n plus 20. And remember, we're trying to see if this is less than or equal to 1. And so we can continue this by manipulating that denominator. So we have n squared plus 8n plus 12. And let's say we manipulate n squared plus 9n plus 20 to give us the numerator. So let's say that's n squared plus 8n plus, 12. Okay, and then what was left over? Well, we took out an 8n, so really we have a plus n. Okay, and then we took out 12 from 20, so really we have a plus 8 left at the end. So if we manipulate it this way, we notice that the denominator is going to be larger than the numerator. And since the denominator is larger than the numerator, then that proves that when we look at this ratio, this is going to be less than or equal to 1. Okay, so again, this additional n plus 8 tells us that the denominator is larger than the numerator, okay, which proves that this is less than or equal to 1. And so since both of those conditions are met, then we say, therefore, the series converges by the alternating series test. And then we got our answer. Okay, so that was number 2. Let's look at number 3. Okay, on number 3, notice we have our alternating series, which means everything left over is our a sub n. And so our first condition is we are trying to see if the limit as n approaches infinity of a sub n, which is n plus 7 over n, is equal to 0. Well, if we did this using the horizontal asymptote, we only really care about those highest degrees. So really we have n over n. Okay, and then if we look at the coefficients in front of that, we get 1. That is not equal to 0, okay, which means that we disproved the first condition. So it's no longer convergent. That means this is divergent. And I want to make this very clear here. Okay, so I'm saying, therefore, the alternating series tests doesn't meet conditions. Okay. This implies that it diverges, okay, due to the nth term test. Okay, so I had to, in my justification, show that there is a reason, another reason why it's diverging. So if you remember the nth term test, the nth term test said as long as the limit as n approaches infinity of a sub n is not equal to 0, then we know that the series diverges. So just make sure you include both parts in your justification. Okay, now let's look at number 4. So number 4 looks a little different. It's not obvious that it's an alternating series. However, it is. Okay, the reason it is based off of cosine of n pi. So again, this is going to be alternating because let's say we plug in some numbers for n. So if we have just cosine of pi, that's going to be -1. Cosine of 2 pi is +1. Cosine of 3 pi is -1. Cosine of 4 pi is +1, and we could continue that forever and see that it is alternating between -1, 1, -1, 1, etc. Okay, so it is alternating. So which means we can use the alternating series test to try to prove that it is converging. And then here are a sub n, you should recognize as the harmonic p-series. Okay, so because of these two things, we actually are going to end up proving that it converges the same way we proved that number 1 converges. Because remember, we said if it's an alternating harmonic p-series, okay, then it's going to converge. So we can continue to prove that just by proving the conditions. So the limit as n approaches infinity of a sub n equals 0. Okay, we already know that. And then for the next one, we know that 1 over n decreases, okay, which is a sub n, so that proves that condition. So we say, therefore, the series converges by the alternating series test. Okay, and then the last one, number 5 here. It says the following is not an alternating series. Look carefully to see if you can tell why not. Okay, so since this is a video and we're not in class doing this, I want you to pause the video. I want you to turn to your neighbor and I want you to discuss with them, take about 30 seconds, and explain why this is not an alternating series, even though I see clearly that it has two alternating series within it. Okay, so pause it, come back 30 seconds after the discussion, and then unpause it. Okay, so the reason why this is not an alternating series, so I'm going to zoom in here. I see an alternating series here, and I also see an alternating series here, which means that the remainder part is going to be my A sub n. So the reason why is because since we have two alternating series, if we were to check each one, we would notice that they would end up canceling each other out and remain positive. So we would no longer go from positive to negative, negative to positive, etc. They're going to cancel each other out. And so to prove this, off to the side, we're going to plug in 1, plug in 2, plug in 3, and see what happens. So negative 1 to the first power times cosine to 1 pi is going to be negative 1 times negative 1, which is 1. Then we plug in 2, and we get 1 times 1, which is 1. Let's plug in 3 for n. Again, we get negative 1 times negative 1, which is 1. So notice that all of these here are positive, which means the values are not alternating back and forth. So even though we have two alternating functions here, together they cancel each other out and remain positive. Also, if we look at a sub n, which is n over n squared plus 1, no matter what n value we plug in, we're again going to get something that is always positive. So that is the reason why this is not an alternating series.